I gave you a homework problem where you have to do some MATLAB work in processing a signal that has interference tones, and you have to design some filters. It's very similar to the previous homework where you design some filters, but this time you have to use MATLAB. So it's useful to give you a few background pointers in MATLAB. Um, First of all, this is all review, so I'll go kind of fast. The part that isn't review is if we have two interference tones. Um, okay, let's suppose there's a tone at 100 hertz and at 200 hertz, and the sample rate is 1,000 hertz. This is a little different than the homework problem because I don't want to make it too easy. So the spectrum looks like this. This is the desired part, the smooth part, and the two tones are at 100 and 200 hertz. We can remove these tones by using two different filters in a cascade configuration. So the first one will notch out the first interference tone, and the second one will notch out the second interference tone. And we can also combine these two filters into one common filter. And we would do that just since we're in the Z domain, we can just multiply them together and we get a notch filter that's got two notches. Okay, so alright, here's the review of design for an FIR filter. It's got all zeros, poles at the origin. It's got two poles to match the two zeros, but if there's poles at the origin, remember we don't count them. So we call this an all zero filter. The zeros are placed, if we want to notch at a mega naught, the zeros are placed on the unit circle at a mega naught and minus a mega naught. So to write that in terms of h of z, we get z minus e to the j omega naught. So clearly when z equals e to the j omega naught, that's a zero. That's that zero right there. And this represents the conjugate zero. We need conjugate pairs in order to have a real filter. And then if we combine using Euler's identity the two complex exponents and divide through by z squared, we get a 1 minus 2 cos omega naught z to the minus 1 and z to the minus 2. So that's a basic FIR notch filter. If we want to cascade two notch filters, we just multiply them together in the frequency domain, or we can convolve their impulse responses. And remember that for FIR filters, the impulse response function, the h's, are the same as the b coefficients. They're identical. Okay, so we could convolve these coefficients. There's b0, there's b1, and 1 is b2. Okay. Well, for example, suppose omega 1 and omega 2, the two notches. Well, we already have this. That whenever in discrete time, to make a discrete time filter, you always operate in using normalized frequency. Okay, this is the most common mistake I see. People forget to normalize the frequency. When you're in discrete time, use normalized frequency. So omega is 2 pi times the frequency normalized by the sample rate. So that's 0.2 pi. The second notch needs to be at 0.4 pi. To get the overall filter, we want to convolve the two sets of coefficients. So this is MATLAB speak here. There's the first coefficient, the second coefficient. We might as well have MATLAB compute the cosine. So we put in W1, we'll call it W. MATLAB doesn't do omega. And then 1. And then the same thing for the second filter. So those are the filter coefficients for the second notch and for the first notch. And if we want to find the overall filter, we just use the MATLAB convolve function, and those should be B's. And just convolve them together. Okay, here I am showing a MATLAB window. Let me drag it up here, and I've actually typed this into the edit window. So I've got all of those commands I just showed you. There's the two B sets of B coefficients. There's the convolve function. If I push the F9 key, which I'm going to do, it's going to convolve those together, and I don't have a semicolon there, so we'll see the output of this convolution. Okay, so there is the set of B coefficients for the overall filter. And what I'm going to do is take those and write them into h of z. Okay, here's h of z, and I just typed those in. I left out some significant digits and just showed a few of them. And there's h of z that we get for the overall notch filter. Let me go back to MATLAB. We can see what this looks like in the z-plane with the z-plane command. We give the b coefficients and the a coefficients. Well, there aren't any. There's just one. And if I push the F9 key, we should get a z-plane plot. And it shows that the two zeros are just where we want them, and on the unit circle. And so this will give us two notches at 100 and 200 hertz. Okay, here's a review of IIR filter design. For the IIR filter, we now want to move the two poles that were at the origin. We move them out so they're at the same angle as the zeros. So we still have a notch. The zeros are on the unit circle. That causes a notch. But the poles are right behind them, and we'll see that this makes for a much better frequency response. There's the h of z, just like always, and now we've written it in terms of z inverse, and we've combined the complex exponents. So this is the standard form for a notch filter, an IIR notch filter, and that's let me erase that and make that a little bit better. That should be r squared. My eraser's not working very well. Okay, here we go. So I'm going to make that r squared. It wasn't written very well. So there's r squared in the denominator. Alright, so the better notch filters are when r is 0.95. So this distance out there is 0.95. So, or it's a number close to 1. And you can experiment with this in the homework. So here we build up the b coefficients. The b's look exactly the same as they did for FIR. And here's the a coefficients. I told a lie. This is not r squared. It was right to begin with. It is just a 2. Sorry, that was right to begin with. And so we have a 2 here. 2r times cos omega 1, and then for the second filter we've got minus 2 cos omega 2 for the b, and minus 2r cos omega 2 for the IIR filter. And we have an r squared term there. Well, if we want to combine this system, note that h of z is the product of h1 and h2. And if we talk about just the numerator part, we've got b1 and b2 of z, and the denominator part is a1 and a2 of z. And just like we did before, we can convolve the b coefficients to get the overall b coefficients. And we can also convolve the a coefficients. If you think about it, this isn't too hard to understand, to get the overall a coefficients. And let's just pop over to the MATLAB, and here I am in a MATLAB window, and I'll just I've already typed this stuff in. I'll just select it, and I'll hit the F9 key, and we see the coefficients now for the a part, the a coefficients. The b coefficients are the same as they were, and so when I write those in terms, if I fill these into h of z, we get the b coefficients and the a coefficients. So it's much easier to have MATLAB multiply these polynomials using convolution than it is to do it by hand. We're also interesting, to look at the z-plane to make sure everything's right. And what I forgot to do last time is plot the frequency response, but I'll do it now. Okay, so there's the a coefficients, there's the b coefficients. Let's look at the z-plane. I'll hit the F9 key, and now you can see that the poles are right up against the zeros. Oops, right there. Okay, and let's go back to MATLAB. I'm going to plot out the frequency response, and we can get that with the freq_z command. We give it the b and the a coefficients, and it calculates the magnitude and phase, which it puts in capital H, and the frequency vector in W, and then we'll plot the magnitude response. The figure, this figure GCF command, just brings the current figure to the foreground. So I'm going to hit the F9 key, and we should see the frequency response. And it's a very nice. This is as a function of radian frequency, so that should correspond to 100 and 200 hertz. So it's a very nice kind of a notch filter. And by the way, let me go back up and plot the frequency response for the FIR filter, and we'll see it's not nearly as good. Here's the frequency response for it. We still have a notch at 100 and 200 hertz. You can see them right there, but this is not flat at all. It's an awful kind of a magnitude frequency response. The only good thing you can say about it is that we've got zero response at the notch frequencies. Okay, a few last minute notes. If you're going to apply this filter to actual data, we could write out the difference equation. For example, for our FIR case, the H1, the first notch, has a real simple difference equation. We could put that into a for loop in MATLAB and actually go through and calculate these samples one by one. But MATLAB is much better at doing vector operations. So in MATLAB, the way we do this very quickly is this is still doing a cascade. We'd apply the first filter. That generates Y1. Okay, so, and we use the filter command. We give it the B and the A coefficients, and X is the input data, and the output is Y1. Right, that's that. And then we feed this output into the filter command with B2 and A2, and that gives us the overall output. Okay, so that's how to implement a cascade. Alternatively, we could have just said Y2 is equal to filter of B comma A, since we've and then give it the input since we've calculated the overall B and A coefficients. But that's not how the homework problem is given. Okay, a few last minute notes about MATLAB. When you first get into MATLAB, look up here. This screen will actually look a little bit different than the screen you'll have, because this is an old version of MATLAB. I can't afford to get the new version. But the first thing you want to do is you'll download the data set from the class website and put it into a directory wherever you want to put it. And then you need to go, when you turn on MATLAB, you need to change the current directory. Like it always defaults to the MATLAB directory, but you need to change this directory to be the one where you've downloaded the data. And you can do that by pushing the ... button. And on my computer, my data is all located on, if I can find it, so there it is. My data is all located on a Dropbox, and there's the place where I keep all my data in the EE320 directory. And so once you do that, then MATLAB will be looking in this directory, and we can do things like load the data set that you've downloaded and you need to process. And I think it's and you can do things like do a dir and do a dir of star.wave to find out which files are available. And then I would say like x comma fs to load me and mama, which is the file you need for the homework. You load it like that, and then you can play it. Which I don't think I'll play because it goes on too long. But it's but anyway, that's all I got. And we'll talk more about this on Monday. Don't forget to look at the short homework problem that's due Monday. That's appended to the note file on the website.